the polymesh folder. And lastly, we had meshed the pipe and we had seen the result using paraview. Okay. Then again, now I am changing the location. Now I am changing the location and then again executing the command snappy xmesh. So actually now the snappy xmesh command will be executed by looking at the geometry that is created latest. Okay, that's a pipe. And also we had seen that the point 000 is lying outside the pipe. So that's why it's showing error. Okay. So what do we want to do? We want to start from the beginning. Okay, we want to start from the beginning.
Delete the folder
Yeah,
polymesh.
we need to delete the full polymesh. We need to delete the full polymesh and start from block mesh. Some problem. Yes, so please delete that. Okay, please delete that folder and start from the beginning. Okay, please delete the folder named polymesh and then start from the first command, that is start from block mesh. Then surface feature extract. Yeah, I wasn't able to. I was not able to delete that polymesh. That's why it's showing the error again. So now the meshing is going on. Okay. So let's see how the mesh will look like after meshing.
So the mesh is created on the block, outer block.
Yeah, mesh is cleared out of the box. So you can take a clip. Okay, similar to what we had shown in the morning. for creating slides. We can create a clip for seeing that. Okay. So inside should be hollow. That pipe region should be removed.
Yes, sir. It's without the pipe section.
Yeah, yes, that's it. What about others? Are you people doing? So how many of you here are familiar with the ANSYS? Please do comment. How many of you are familiar with ANSYS? Oh, Nilesh. So, Nilesh, your first attempt in CFD software is OpenFOAM. Very good.
Yes,
Yeah,
sir.
Jidin. Yeah, okay. Jidin. Yeah,
Sir,
what
I've
about
tried
others?
Inventor, but in there it was I couldn't raise to that level.
Oh, okay, okay. But Inventor doesn't have that much
But
features.
yeah, it doesn't have CFD also, I guess.
Yeah, yes, yes. some small analysis can be done in Inventor.
Yes, sir.
So only two responses. What about others? 12 are there and two responses. Yes. Again, nine more. Oh, there are many don't know answers. Okay, see one thing. If you are undergraduate students, what I would say for postgraduate also, what I would say is that you should know some of the softwares that can be useful in our career. Okay, so one such software is MATLAB. So using MATLAB, we can do basics of programming. Then another software is ANSYS. Because yeah, you are studying OpenFOAM, that's also based on CFD, and uh, another software is ANSYS. It's a commercial software, but cracked version is available. Okay, cracked versions are available, so we can install that. But anyways, just have a try on ANSYS also, because we also want to know how it look like or how can we solve the things using ANSYS. Okay, so just Google it. You can watch some YouTube videos and all. And it's very easy, not like this, because it's having a graphical user interface. So you will be able to see all the things. You can just click only, or already all the things are will be there. Some drop down boxes will be there. You can select from that. So it's user friendly and not like this open form. So just try to study the basics of ANSYS also and just compare with the open form. Okay. Don't blindly study open form. I won't recommend that. Okay. But it's good. Studying open form is always good and it will be useful in our research work always. And if you could do some BTech courses also, that's fine because we'll be studying something at least. Okay. Even though we are doing a small project work, we will be studying at least about that specific thing. Okay. So we had completed meshing and let's see how it looks like. So this is our mesh and just I can see that pipe inside, which will be carved from this domain. Okay, actually there is no pipe in that. So just we can see how it look like. Okay, I'm taking a clip now. So just select the uh, geometry and then click on the clip And then again, as I had shown in the morning, I am going for Z normal because I want to see the entire section. So I click on the Z normal and then I am clicking on apply. So now I will be getting a clip and I am just closing that plane, clipping plane, and I only want to wish the clip now. See, see, this is the mesh that we had created. Okay, this is the mesh that we had created now, and we can watch it with surface with edges also. See, this is the place that we had meshed. And one more thing, if we look at this area, if we look at this area, we can see some refinement. Okay, we can see some refinement at some particular region only. It's just because we had created a refinement region cylinder early, isn't it? And the diameter that we are given was 0.05. The diameter that we are given was 0.05. And the diameter of the pipe is roughly 0.03. Okay, the diameter of the pipe is roughly 0.03. No, I think the radius, sorry. The radius that we were given was 0.05 and the radius of the pipe is roughly 0.03. So there should be some region outside the pipe also. Now we had removed all the pipe portion and there was some remaining portion in that particular refinement cylinder. Okay, there was some region between this pipe and this refined cylinder, that invisible cylinder that we had created. So that portion is being refined now. Okay, that portion is being refined now. And also remember one thing, in that refinement region, we had given the command as inside. Okay, so inside that particular cylinder only, the refinement will be done. Okay, inside that cylinder only, the refinement will be done. So in this particular case, we can clearly visible that. Okay, so this was the cylinder, and inside that portion is being refined. Okay, inside that portion is being refined, but still there are a lot of spaces outside that cylinder region which is not refined. Okay, these are the regions where it's not refined, but this is the outside the cylinder region. So if I had given the command as outside the cylinder, then those portions will be refined. Okay, those portions will be refined. So in some situations we come across like those things because we want to refine a region which is outside that particular area. Okay, so at those times we want to specify the command as outside. Okay, then only we'll be able to refine the outside surface of that particular cylinder. Okay, so that's it about the meshing and refinement process. So now we had learned about meshing the geometry and meshing the domain. Okay, at some cases in CFD analysis, we need to mesh the domain. Okay, we don't want to analyze the what to say. Don't want to analyze the geometries. Such example was our aerofoil case. Then in the case of nozzle, a flow through the nozzle, the shock waves and all. When we are dealing with that things, we want to mesh the geometries. Sorry, the domains. Then flow or a cylinder. Then again we want to mesh the domain. Then suppose we are trying to um, find a flow or a body or something like that, or we'll be meshing the domains. But in some cases, in the case of some heat transfer problems or fluid flow problems in which the fluid is flowing inside the geometry, then obviously we need to mesh the geometry. Okay, so that's one case. And in some cases, we don't want to create the geometry also as a CAD geometry. And we can use the block mesh itself. We can use the block mesh itself for creating the geometry. We don't want any softwares like AutoCAD or SolidWorks for creating the geometries in that particular case. Even we can model a pipe also using block mesh, but it's quite difficult. We need to give all the vertexes, then or it should be arranged in some sort of manner, and everything is quite difficult. Okay, but anyways, we'll be dealing with that thing for creating a small geometry for analyzing the heat transfer problem. Okay. So in that we'll be studying about one more dictionary file called Topposite Dictionary. Okay. So this Topposite Dictionary will be used for creating the geometry in that particular case. So that's it about the machine thing. So if you have any doubts, you can ask now.
Sir, you will be doing analysis in this model or another model. This is only
Yeah,
for
in this model, in this model, we'll be doing one analysis, and
this will be an external flow problem, no, sir. In this case, if you are
no,
eliminating the pipe section, that means
no. I mean, I will be doing the analysis in the pipe flow problem. That means not
okay.
this particular mesh.
Okay. So
Okay.
for making for the creating the flow mesh, then we need to mesh only
Uh,
the pipe part, no?
yes, we need to measure only the pipe part. Yes, exactly.
Okay. So we don't want
Okay.
any domain in this case.
No,
In
we
that
don't
case.
want the domain. No, we don't want any domain.
Okay. Sir.
Okay.
So
Any
is
more?
it necessary to make this boundary outside the pipe in order to analyze?
No, in this particular case, we don't want it. But suppose we are modeling a pillar, okay, and we want to analyze the flow across that pillar. Uh,
Hmm.
Let it be a column of a bridge, pier of a bridge. Okay, so the water is flowing through that the water is flowing through that cylindrical portion, and we want to analyze how it's affecting the flow of water or how the vortices are being created, etc. So that's a problem with the flow past cylinder. Okay, in that particular case, we want to measure the domain. And in the case of an aerofoil, what happens? Aerofoil is actually see the aeroplane is flying through the air, isn't it?
Yes, sir.
Yeah, but actually we are keeping the aeroplane as stationary, and we are giving the velocity to the air. Same effect, isn't
Hmm.
it? Then if you want to analyze the aerodynamics of a car, the same thing we are doing. We are modeling a car and we are measuring the domain outside the car. Okay.
Okay.
And then we are giving some velocity to the air. That means outside the domain, we are giving some velocity to the air so that the air will be flowing through this what we call surface of the car, and we can analyze aerodynamics. Okay.
Okay.
So in those cases, we'll be measuring the domain.
Okay.
Okay.
Thank you.
So to see the mesh in Paraview, what was the extension, sir?
Actually, that was not the extension for seeing the mesh. Actually, the we want to save the result file. We want to save the result file in an extension called FOA form. Okay. So what all things that we are executing and what all things that we are getting will be saved in that file. Okay, that file extension name is called .foam, and we can give a file name what all we like. Okay, and the command is that touch. Command for creating that file is touch, touch. So here we had given the file name as result. So for executing the for creating that file, we will be executing the command touch space result.form. Okay. So what all things that we are doing will be saved into that file. So first of all, we had created block mesh. Then again, we can see that block mesh using that same file. Then I had meshed now. I am seeing the meshed geometry using that particular file. Now in the next step, I am doing the I am solving this problem, isn't it? So after solution, I'll be getting results. Maybe some velocities or uh, some pressure values will be getting, and I can visualize the same thing using the same file itself. Okay, what all things that we are doing is will be saved in that. Okay, so there is no particular thing to see the mesh like that.
Sir, I tried another problem at home.
Uh-huh.
So I created one uh, what rectangular prism.
Okay,
The bottom face, one of the side face is considered as wall, and bottom and side face is considered as wall, and top and
okay,
the another side face is considered symmetric face.
okay,
Actually, I'm trying to uh, analyze a fluid flow inside that rectangular prism. So when I created mesh files
mm.
inside the constant, the folder inside the constant, I got uh, I was trying to create block mesh.
Okay,
So inside the constant folder,
mm.
there was a folder called polymesh.
Yeah.
So in order to see the mesh, what should be the command I should? That is what I'm asking.
Oh, okay, fine. In order to see that mesh that you have created, just save a result called touch.form. Okay, touch file name.form, save a result file like that, and you can open that file for viewing the result.
Once more, sir. Is there anything I need to type in the terminal?
Yeah, you want to type, I will show you once again. Oh, sorry. See, you are telling about this folder. Okay,
Yes.
yeah. But in order to visualize that, after executing the command block mesh,
Yes.
what we need to do is that we need to create a form file, FOAM.
FOA.
Okay. So that file contains all the results that we are getting after each and every execution.
Okay.
Okay. So in our case, we had created a file
How
called
we are creating that form file? How we will
yeah.
create that?
In this particular case, the file that we had created contains the name result.form. Okay.
Okay.
So in order to create that, we are giving the command touch result.form. Result is the name of that particular file. You can give it as X or Y or Z. Okay, it doesn't matter. But the extension should be .form.
Okay.
So after executing the command block mesh, you want to create a file called touch.form, touch file name.form. Then open that file using paraview. You will be able to see the block
Okay. Touch file name dot form.
dot form. Touch after touch there should be a space. Okay, touch space file name.form.
Okay.
Okay. And
Then
yeah, once this file is created, no need to create it again and again. Okay. Once we had created a file called this .form file is being created in our case file.
okay.
And after even though after creating this file, we are executing some commands, automatically those results will be saved in this file.
Okay. Now
Okay.
I have reached up to setting the boundary conditions in that problem. Okay.
Oh,
Just I
that's good.
tried a problem yesterday.
Okay.
So
Okay.
I don't have created this form file. So whether
Mhm.
I will be able to see the mesh file now also after
Yeah,
creating
now
this.
also you'll be able to see the file. That will be the final geometry file. We cannot see that step by step. Okay.
Okay. That means we will
Uh,
be only seeing the meshing thing because I have not done the analysis part. I just
yeah,
created the geometry and
given
meshed
the
it
boundary
and just
conditions.
applied some boundary conditions.
Okay, okay, fine. So you will
But
be seeing the machine part only now.
meshing part.
Yes.
So I need to type TOUCH
TOUCH, yes.
capital F
No,
FILE.
no, TOUCH
Okay.
space
Okay.
file name can be any name. Dot
Okay.
FOAM. FOAM should be small letter.
Okay. Okay.
Okay. Everything, the command and the extension should be small letters.
Okay. Where this file will be created actually? In which
That will
folder?
be created in the case file. So that
Okay.
the terminal should be actually present inside that case file. Okay, path should be Suppose in our case that is airfoil 2D. So the path of the terminal should be inside the airfoil 2D. Then only we need to execute the command.
Okay.
Okay.
Okay. So for to be in that path, you should be cd that file name.
Yes, CD that path. CD space that path.
Okay. Actually, we were new to this OpenFOAM. That is why we are just
Ah,
creating only.
it's okay. No issues. Some problem with my virtual box. Yeah, any more doubts?
Sir,
Yeah.
so if we want to do the testing on an assembly part, then we just need to open the assembly or the entire file should get present.
Assembly means geometry.
Yeah, I mean I've made different parts and assembled it, and then I will be opening it in that Salome to create the coordinates.
Okay.
Then should I need to use all the parts there, files of the all the parts, or just the assembly one?
Just the assembly one, that's enough.
Okay.
Then again, you want to export that. Okay. In Salome, you want to explore all the surfaces and then we need to group according to our patch names and then we want to export that in the still format. Then again, combine those all files into a single file as we did in the case of PipeFlow and
Yes,
then
yes.
save the try surface.
Okay. Thank you, sir.
Yeah. Now I am just remeshing that to our early stage. So I'm going to mesh the pipe. Okay. Now I'm going to mesh the pipe. So anyone remember what's the location inside the pipe? Anyone remember? Location of the pipe.
So minus zero, sorry, 0.015.
Yeah.
Last one was 0.03. Last point was
Zero,
0.03.
zero. Last one.
Yes, sir. Third point. Second one, I'm not sure.
Uh, Last point, I'm not sure about that. I think third one, second one will be some mine something like that. Okay, let's
I
see.
remember 2 points. One was 0.015. The other
0.05
one
and
was 0.03.
0.03.
Yes, sir. But I
Oh,
don't know the order. Which one was
okay, okay.
0.03? Second one or the third one?
Yeah, yeah, that might be second one. Let's see. So I am giving the values and I am executing the command once again. Let's see. So first of all, before going to that, I want to delete the polymesh or else the same error will be occurring again. Because we are giving the location measures inside the pipe and now it won't recognize that pipe because already that is removed from the. So block mesh. Yeah, somewhere. Yeah, I think the path is not good. Yeah, the path is not good. Yeah, now block mesh. Then surface feature extract. NAT mesh minus override. So now we are meshing our final geometry. Now after meshing, we'll be moving on to the analysis part. And today we'll be discussing some basics about the giving boundary conditions and all. And then later tomorrow morning we can do the hands-on on that. Yeah, I have one question to this undergraduates. Had you started your BTech project?
No, sir.
You people are
I have
the
to.
final year, isn't it?
Yes, I have to start it in this semester
Oh,
only.
okay.
So in the last semester, I've made an aeroplane on Inventor.
Oh, that's good.
I was thinking I can analyze it for the project in this semester on
Oh, that will
OpenFOAM.
be too difficult.
I will try. Let's see.
Yeah, actually the problem is that it needs a lot of measures. So the domain should be large
Yes, sir.
and it will take a lot of time for computation.
So I've made like not exactly the aeroplane, but I've made the airfoil, Naka airfoil
Ah,
23170,
okay.
and the the sketch of the body part.
Okay, okay.
So
But in the
I
case of
was thinking,
airfoil, yeah, in the case of
yes, sir.
airfoil analysis itself, we will be analyzing the 2D of neck airfoil only because that
Yes,
is
sir.
itself take much time.
Okay,
So the computation is quite difficult. Means we want high configuration computers for that.
okay. And I'm studying FEM also in this semester.
Uh, that's good. One of my research work is in the case of IC engines. So once I had tried to do a CFD analysis on this IC engine, and in ANSYS it has a special package for analyzing this thing. And I had tried to do it in my computer, and it was nearly impossible for that particular piece. It got hang. And then later on, I had got one system from IIT Madras, access over there in a workstation. It's having some 512 GB RAM, 512 GB RAM, and 20 cores. Then in that system itself, I had run for 50 days continuously, 24 into 7 like. Then also I didn't get the result. Later I dropped that plan.
So in the last semester, my team and I were making that chassis design for F1 car, and we were
Oh,
analyzing it on ANSYS. That also took like
okay.
15 to 20 minutes just for the meshing.
Yeah. Uh, But that's very less time. For machine 20 minutes, that's okay. But
So there
uh,
was only the chassis part, nothing else.
hmm. Even a pipe, if we are analyzing a pipe with solar and all, it will also take, sometimes it will take 1 hour or 2 hours, or it may take 1 day for machines. So that depends on the computer also, the
Yes, sir.
system what we are using.
So
Yeah, you can.
in the in when I'm doing block mesh in one of the geometry, in the script there was one convert to meters. It is
Yeah.
given as 0.01 as a scaling. There is 0.01 is a scaling factor. What does that scaling factor actually mean by zero
The,
zero one? We can
one means,
reach
yeah,
meters.
one means it's in meter. Okay. So if the converter meters is given as one,
Okay,
all the coordinates that will be given by us will be in meters.
okay,
Okay. So now I am giving the converter to meters as 0.01.
okay.
So what is 1 by 100 of a meter?
That is, it will be centimeter in one
Yeah,
by
it will
hundred.
be centimeter. So all the vertexes that will be given by us will be in the centimeters.
Okay.
Okay. If it is in the 0.001, that will be in millimeters.
Also, in when giving hexagonal values,
Okay.
there is a division grading. Say it is some values should be input as a division grading.
Yeah.
So what is that value, sir? Three values are
Uh,
given.
yes. That's in grading. That means that's a right end, isn't it? Right end of that
Yes,
line.
to the right
Yeah.
end, to the right
Yeah.
end.
Yes. That's the just the ratio of the length of the final element and the initial element in that particular direction.
Okay, so
Okay.
actually
So
the cell will be growing.
no, it's not. It won't be joined. That means in the block mesh we are dividing those blocks. Okay.
Actually,
Dividing.
in my case, it is 20 centimeter length and
Okay.
width and height is 10 centimeter. And the
Okay.
grading
Suppose
given is 133.
133. Okay. That means suppose in the x direction. Suppose in the
X
x
direction is
direction.
20
X
centimeter.
is in the 20. Okay. What about y end is it?
10, 10.
10, 10. Okay. In y end is it, if we are giving the grading as 3, that means
Okay.
the first element in the y direction and z direction, you are dividing into some sort of different elements that you will be specifying in the second command of that particular line. One more
Yes.
bracket will be there, isn't it?
Yes, that is
So there you
actually the
can,
number of divisions.
yeah,
So
number
in
of
X
divisions.
direction, I have given 100 division. Y and Z direction, 10, 10 divisions.
Okay. So you are dividing that y and z direction with these 10 divisions and
Yes.
that particular one, first division and the 10th division. Okay.
Uh-huh.
First division and the 10th division's length will be having the ratio of 3.
Okay, okay.
Okay. That's what is meant by gradient 3. Or if you are giving the 1 as the value, then all the length will be same. All the elements length will be same.
Okay. That means
Okay.
the final division will be three times that of the first one.
Yes, first one. Yes.
Three times. Or 1
Three
by 3
times.
or
Three
3.
times. Three times.
Three
Three
times.
times.
Okay, sir.
Okay.
So I'll be discussing the boundary condition part now
Yeah.
later.
Yeah. Now we are moving on to that. So I just want to complete this one. I just see whether it is completed or not. Yeah, it's completed. So now we can move on to the solver part. So I will give a presentation based on that now, and later we will be doing hands-on tomorrow. So some of the things that we had discussed already we had discussed. So I will just rush on through the things. So what are things that we will be dealing in this presentation is uh, how we can provide a fluid type, then what are the boundary conditions, and how we can run it parallelly. Parallelly, I will just show you because it's very risky to run parallel in this virtual systems. So I will show how to run parallel. Uh, I cannot simulate that. Now, as I discussed earlier, we have three folders in a case file, that is zero constant and system. And now we are almost familiar about most of the files, and we'll be coming across to the files like control dictionary, then a polymesh folder, etc. later on while we are giving the boundary conditions. So we'll be discussing in detail at the time. Now, in a simple flow problem, will be having three files called new t, new tilde, p, and u. Okay, so u, the file name called u represents the velocity parameters that you want to give. P represents the pressure parameters. Then new tilde is the turbulent kinematic viscosity, and nu t is the turbulent viscosity. Okay, so these are the things that we need to give in the boundary conditions or the initial conditions that will be present inside the folder 0. So these things will be depending upon the type of analysis that we are doing. Okay, in the heat transfer problems and all, we will be having temperature also. Okay, now in the case of a polymesh folder will be having the boundaries. So before we are creating this initial and final conditions, the initial condition and the boundary conditions, we will be checking this polymesh folder. Okay, in the polymesh folder, we will be having a file name called boundaries. So after meshing, while checking this boundary file, we'll be able to know how many patches are there and what are the name of those patches. So sometimes some of the patches will not be removed after meshing, so that we need to check it out. Okay. Suppose in our case, uh, we had created a block mesh, and the block mesh will be having six patches, if it is not grouped. Okay. If it is not grouped, the block mesh will be having six patches. That means six phases. And we have three patches for our pipe. That means inlet, outlet, and wall. So altogether we have nine patches. And at times meshing. So altogether there are nine patches, and all these nine patches will be inside that particular boundary file. Okay, inside the polymesh folder. So it will be showing the total count as nine, and this each patch will be named in that. So default name for this block mesh is min x, max x, min y, max y, min z, and max z. Correspondingly, the minimum and the maximum phases in that particular directions. In addition to that, we will be having this full node, full inlet, full outlet. Okay, all these things will be named order, and the total count will be given there. And we know that we want only three boundaries, and obviously we will be giving the or naming these things in our initial condition or directory for this pressure and velocity or temperature values. We will be specifying these three patches, and we will be giving some values or boundary conditions. And finally, we will be running the solution. Then the error comes, because already in the polymesh folder, it specified that we have nine patches, and we had given only boundary conditions for three patches. So six is remaining. Okay. So always we should just cross check this while doing this boundary conditions. Okay. So sometimes some unwanted patches will be present inside that. So we need to remove that before going for the analysis. That's one thing that we want to do. Now next is about the tri-surface folder and all. That's past. That's already we have discussed. Then about the transport properties. In the transport properties, we will be giving the properties of the fluid that we are using. So in the fluid flow problem, basic flow problem, it will be containing only density and viscosity. Then in the turbulent property, either we can give it as a laminar or we can give it as a turbulent flow. Then what turbulent model that we want to use, that we need to specify over there. So that's about the turbulent properties. So these are the files or the folders that's contained in the constant form. Now we are moving on to the system. So in the block mesh dictionary, that's already we had discussed half. Some more is remaining that I'll be discussing in the later while we are doing the heat transfer problem. Then we have a control dictionary. Every control is within that. What type of solver we need to use, what is the initial time step that we want to start from, till what time step the solution need to run, and what is the time interval that we want to give, at what time interval we need to write the solution. So everything is in that. Then a decomposed part dictionary is there that's used for decomposing the geometry into several parts so that we can analyze that parallelly. Okay, we can run parallelly. So for that particular purpose only we are using this decomposed part dictionary. And we have FC schemes and solutions, that is the solution schemes or the methods that you want to use. Then snappy XMesh dictionary is there, surface feature exact dictionary is there. All these things we had discussed already. Now about the solvers. While I had shown some examples in the case of uh, incompressible flow, while we are copying that folder, you might have come across with this different types of solvers, icoform, simple form, pimple form, etc. You might have seen some folders having these names. So all these are different types of solvers. So first one is icoform. So that is used in the case of unsteady incompressible laminar flows, in the case of Newtonian fluids. So that it uses PISO algorithm. That means pressure implicit splitting operator algorithm to solve the icoform. So the basic governing equations are continuity equation and the moment equation. So PISO algorithm will be used for solving the momentum and continuity equations. So what are the procedures that adopt? Let's see. So initially, it's guessing some value for pressure. And then the flux value, that velocity value will be taken from the previous value. At the initial condition, it will be taken from the initial value that's specified. Then using that velocity predictor, it will be solving the moment equation. And the moment equation is solved to get the velocities in the x, y, and z directions. So initially we are used the pressure as a guess. So the remaining variable is velocities, and the velocities is being solved now. Then again, by using this velocity, we are solving back the pressure because initially we only guess the value. We don't know the exact value. So then we are going to solve that pressure. Then just the flux equation, this continuity equation is being again corrected according to the new pressure and velocity values. And this process goes on. And this process goes on until the convergence is reached. The convergence means it will be comparing with the previous value. It will be comparing with the previous value for getting the errors. And the error is huge. Here, this process goes on until it's met with the convergence. Convergence can be some error value. We can give the limit as 10 raised to minus 3 or 10 raised to minus 6. So if the difference with the current value and the previous value is within this limit, below 10 raised to minus 6, then we can tell it as the convergence is occurring. So in some cases, it's not quite easy for getting that convergence like that. So what we used to do is that we used to check the result at a particular point after some time or after each time interval. Okay. Say suppose after 1,000 iteration, I am checking a velocity value at a particular point of a pipe. Then after 1,500 iteration, again I am checking the velocity value at that particular point. Again after 2,000 iteration, again I am checking that particular value. And at some point or at some time, we can see that the value is not changing that much. Almost it's remaining constant. Then we can tell that the convergence is okay. our convergence criteria is met. Sometimes it won't get converged like that. It will be a pattern, repeating it again and again, like a cycle. That means after 10,000 iterations, we'll be getting some value. Then we can see that the value goes on increasing with the number of iterations. And after some time, it gets starts reducing. And say after some 12,000 or 15,000 iterations, we will be getting the same value as that of the 10,000 iterations. Again, if we are keeping the same thing, again this process goes on and it comes back to the same value. So it's more or less like behaving cyclically. It never converges. So that we can stop the iteration at that point itself because there is no meaning in keeping running that particular program. So we can tell that as converge. Okay, so these are the some of the things that we'll be doing manually. Then one important thing that we need to keep in mind is that we need to do the what to tell mesh independent study. Okay, we need to do the mesh independent study for doing all these calculations. That means we'll be trying with a different number of meshes for a particular case, and then we need to compare the result. So suppose initially I am giving some 15,000 or 20,000 elements, and I am solving, and I am looking at the velocity or pressure or what are the values I am looking after convergence. Okay. Then now I am giving some elements as 50,000. Then again I am doing running the solution and at the convergence I am getting some results and I am comparing with the previous result for what I had got for the element numbers 20,000. And if it's showing some deviation, I am then again increasing the number of elements and running the same. And at some particular number of elements, we can see that if we increase the number of elements, there is no much change in the result values that we are obtaining. So that should be the element size that sorry, the number of elements that we need to do for the analysis. So that's called machine dependent study. So that also we need to do it manually. Okay. So these are the two things that we need to do manually. But in the while discussing about the solvers, we can tell that how the solver is working. It depends on the convergence criteria and it looks whether it's converged or not, and the iteration will goes on. Okay. So the ICOFOAM generally, without telling about the solver or the procedures that is adopted by the ICOFOAM or the algorithm that's used in the ICOFOAM, generally ICOFOAM is used where the condition is unsteady and the flow is incompressible and the flow is laminar. Okay, so these three things that you need to keep in mind. So if the flow is unsteady, then it's incompressible and it's laminar. Yeah,
Sir,
obviously.
so
Yeah, yes,
so while
yes.
using this solver,
Mm.
we may not be able to capture turbulence values.
No, we are not able to capture the turbulent values.
We are only considering laminar in this
Yeah,
case.
yes, exactly.
There
Yes,
is mu t and mu tilde, which has been discussed in the previous slide. It
yes.
will be equal to zero.
That won't be there while solving the ICO that two folders won't be there, or else that will show error. Okay, this
Okay.
new T
So
and new tilde
turbulence
file,
viscosity and
kinematic
turbulence
viscosity.
viscosity, turbulent kinematic viscosity will be
Yes,
zero.
yes, yes. That should not be zero. That file itself won't be there. Okay, now in this particular folder, we can see two files in the zero folder. That's new T and new tilde. If I am keeping that folder in that zero, I am keeping that file in the zero folder and I am using the solver as ICOFOAM, it will show error because that is unexpected one. ICOFOAM doesn't solve turbulent cases, so it doesn't want those values. So it will tell that some other values are there and it will produce some errors. That's it. Okay.
Okay, sir.
Yeah, Hari Krishna, you are right. The grid independence depends on the mesh quality. So we need to adopt the same methodology for creating the mesh. And in the case of Snappy X mesh, it doesn't matter because already we are giving the quality of the mesh that is expected And that's why it's showing some iterations. We can see some iterations happening while we are executing the command snappyx mesh. Okay, so we have a quality mesh dictionary also. So in that we have specified the quality that we are expecting. So while meshing, this iteration will be happening and it will check whether the quality is met or not. So it doesn't have a, or we don't want to bother about the quality of the mesh that we are creating once we had using this snappy hex mesh, because already we have a quality dictionary file where we have the control over the quality. The only thing we will be doing is that we will be changing the levels. So the level, if we are increasing the number of levels, that means we can reduce the number of elements. That means the element size will be getting increased. So then again, the quality will be same, but we can increase the number of elements. Okay, that's what we are doing in the case of a grid independent study while we are using OpenFOAM. Now, in the case of pisoform, the solver that's used is pressure implicit with splitting of operators. That's a solver that is used in this case. So again, pisoform is used for solving the unsteady problems, incompressible flow problems, and again the turbulent modeling can also be used here. That's RAS and LES simulations can be used. Reynolds average stress and large eddy simulations can be used in this pisoform. Then the that's it's an extension of the symbol algorithm that we'll be dealing now, discussing later. And generally, it looks like it takes more CPU time. That's a little bit problem over there because this LES and the RAS simulations are take little bit time. Then we need some suitable this numerical scheme should be there. So the computationally it's a little bit tough or difficult, and it is time consuming one. So that's why we are using one. But anyhow, if you want to use LES or RAS, the apt solver is pisoform. So it's apt one for solving unsteady, turbulent flow incompressible problems. Now, this is just the layout of showing how this piso is being solved. So first of all, we are solving the discrete moment equation. Then we move to the pressure correction equation, where the pressure is being corrected, and the corrected pressure and the velocity values is being given into the pressure equation again. Then again, this process goes on for correcting the pressure and velocities. And then all the discretized transport equations will be solved there. That means the continuity and moment equations will be solved, and we will be checking for the convergence. And if it's not converged, this process will be happening again and again. So this is a brief about the piso algorithm. Now it's just a comparison of icoform and pisoform. So pisoform includes the declaration for this non-Newtonian fluids also, because in the case of icoform, I had told that it's possible only for Newtonian flow, but in the case of pisoform, we can use that in the case of non-Newtonian turbulent flow also. Then ico is for only laminar flow. Then icoform, we can set the constant kinematic viscosity, while the pisoform, the laminar transport properties will be depending on the models, because it have a space for the non-Newtonian flow also. So we cannot give a constant value of the. Then in the case of icoform, we have a constant kinematic viscosity in moment equation also. While in the case of pisoform, it's not constant, because again the same thing. It can be used in the case of non-Newtonian and turbulent flows. Now we are coming on to a symbol form. Okay, that's what we are using in our case. So its full form is semi-implicit method for pressure linked equation. So that's simple form. So in this one, we are using the steady state solver for incompressible turbulent flow. So that's why in our case we have nu t and nu tilde over there because we are using turbulent flow. In the case of simple form, we can use turbulent flow and it's incompressible. But the problem is that the flow is steady. Okay, it's not time dependent, it's steady. So what are the things that we are following in the case of simple form? First one, we are setting the boundary conditions and then we are computing the pressure and velocity gradients. Then we are discretizing the moment equation and we are solving that. Then we are computing the uncorrected mass fluxes at the phases. That means at the inlet, outlet, etc. Then we are solving the pressure equation, then updating the pressure field throughout the geometry or the nodes. Then again, we are updating the pressure conditions at the boundary. Then with that particular pressure value, again, we are finding the velocities for correcting the mass flux. Then again, at all the cells, we are correcting the velocities and it goes on. So this is the general method that is adopted or the algorithm that's followed in the case of simple form. So please do remember we have three solvers now: icoform, then pisoform, and simple form. Okay, so icoform can be used in the case where the flow is laminar and unsteady, and it can be used only in Newtonian fluids. In the case of pisoform, it can be turbulent, unsteady, and non-Newtonian also. In the case of simple form, it can be used in the case of turbulent flow, incompressible flow, and it should be steady. Okay. So keep in mind while giving the boundary conditions and all. So we need to choose the apt solvers for that particular thing. Now comes the Pimple form. Next one, Pimple form. So it's again used for transient and incompressible flow. Okay. It's used for transient and incompressible flow. So we were discussing about the piso and symbol. So it's a combination of piso and symbol algorithm. Okay, that's why it's called Pimple form. So it's a combination of piso and symbol algorithm. So Pimple form have this. We can able to solve this transient flow problems, and it's used where one of the parameters that we are looking for this conversion criteria is current number. So sometimes the current number goes on increasing, and at a particular point, the solution or the iteration stops, telling that the solution is getting diverged. So while using this Pimple form, even though the current number is getting increased beyond some particular value, the solution goes on. Okay, so it permits for a high current number. Then, then Pimple iterates and underlies the solution of pressure velocity coupling with a time step. That means we can have variable time steps because that's a transient problem. Then in the case, Pimple loop ends by reaching either a static number of iterations or a residual limit. That means this iteration, we can specify some number of iterations. So this will be stopping when that particular value is reached. Or we can give some residual values. Say it should be some 10 raised to minus 6 or 10 raised to minus 5. So this iteration will stops only when that residual value is reached. Okay. So now moving on to the block mesh. Yeah, about the block mesh. One minute. Yeah, Harry, you were telling what? If there is a problem which has scope among all these three solvers discussed, which among should be selected based on convergence. I had discussed this always for different types of conditions, so that that particular physics depends on which solver that we have to solve. For example, if I am dealing with a, a fluid flow problem, simple fluid flow problem, which can be steady and having some low Reynolds number, then it doesn't matter. I can use this simple form. Okay. And if it is having higher Reynolds number also, that may be a turbulent flow, but it is time independent. Then again, I can use this simple form. No problem in that. But suppose it's transient, that means it's unsteady, that changes with the time. Then again, what should I do? I should go to icoform or pisoform. Okay. Then again, there I am thinking, what is a turbulent condition, whether it is laminar or turbulent. So if it is turbulent, I want to use pisoform, transient and turbulent condition. If it is non-neutron or no neutron inflow, that doesn't matter. We can use pisoform. Now, suppose if our case is transient, that's unsteady, and it's laminar, then that's okay, fine. We can use icoform. Okay, so we need to think what our problem is. We don't want to think about the solver. Okay, first of all, we need to fix what should be our problem or what sort of analysis that we are going to do. Then we need to select what type of solver that is best suited for us. Okay. Yeah, what about the turbulence models available? There are a lot of turbulence models available, and there are a lot of equations also for solving that. I will just show that. Just, I think, just Google on. That's it. Because I don't have the total list. I will just show you now. And I will be sharing on PDF file also, because that's a book on just the boundary conditions, Okay. There are a lot of boundary conditions that we can give. Even, I think it's having some more than 100 pages, I think, that book is having. The only discussion is about the boundary conditions and the different formats or what should be the values for that particular boundary conditions, etc. Okay, so I think that's just enough for telling what all sort of things that we can give using this open form. Okay, so such a vast thing is that, or such a flexibility we have in open form. So I'll show you. And for the newcomers, that means for those people who are very new to this open form, you should do one thing. We have some of the blogs is there for open form. Then we have two different websites. That means one openform.org and openform.com is there. Both are different companies that make the software, this open form package. So lot of data are available in those sites. More or less like a guide, you can use that. Okay. See, this is I'm taking from the openform.com. Then CFD direct is there. You can use that also. See, in the case of turbulent properties, you can see, it's not discussing about detail. I will show one more page. See, these are the list of turbulent models that is used. RAS model is there, then LES model is there, then in transport properties also we can give different things. One more website is there. Discussing about only two models. Yeah. See, this CFD direct, this very useful one. In a very detailed manner, we can find everything, each and everything about OpenFOAM in the CFD direct. So, when all you have clarifications required regarding anything, you can just go to this website and everything will be there. Okay, in simple manner, it will be there. And I think it's self-explanatory also. But the problem is that while we come across an error, that will create a problem. That will be a real problem. Okay. So here we can see RAS model is there. Then that's with regard to the symbol form. Then incompressible RAS model is there. See, here we can see the different list, like different equations that can be used for solving the values for this kinematic dissipation of viscosity and kinematic uh, dissipation energy. Okay. See, LRR, Lambros, KE model. So these are a lot of models, turbulence K epsilon models. That's for finding the value of K and epsilon in the case of a turbulent flow. Okay, so these are the different types of models that can be used in different flow conditions. So we need actually before choosing a particular one, we want to go in detail what is being actually happening or what it solves or whether it is fitting in our case or not. Okay, so in detailed manner we need to look into it and then only we want to choose a particular uh, the algorithm or the model that's being used. This is a RAS model. Again, we can see the models for finding the K and epsilon. Then LES. LES also there are a lot of models for finding the stress. Then in the case of this is in the case of compressor flows. Okay, for finding the wall functions. So uh, just use this CFD direct. Okay, so mostly all those things that we are using will be present in that. But I didn't find that much boundary conditions in this CFD direct, so I can share that PDF. Okay, so that will be quite useful for us. Almost all the explanations and everything is there in that particular thing, and we can have the formats also. What should be the format of a particular boundary conditions? That's also there, so we can refer to that while giving the boundary conditions. Okay. So now I am moving back. So I'm not discussing further about this block mesh thing and all. We'll be coming back soon while discussing about the second problem. Yeah, in the case of control dictionary. See, now we are specifying the solver. So the solver is specified here, application. Okay. In the place of application, we are giving it as symbol form. So that means the solver that we are using is symbol form. If we are using that ICO form, we can specify it as ICO form. Okay. Now start from latest time. That means initially that will be starting from the time 0, and after some time we'll be running this iteration, and uh, sometimes we may stop in between without getting the results. Okay. So now I want to start it again. Does we need to start from the beginning? That means from the 0? No, we want to start from the latest place where we have saved that file. Okay, that's why we are giving it as latest time. Then initial start time will be 0 always. Then we are giving the time step delta t. Delta t is the time step given. That's here it's given as 1. Then again time step. Time step means the time interval where the write should be given. Okay, that means write control. Write control is given as time step. That means at every time step the solutions will be written in a particular file. Then the precision. Precision is given as 6. That means the number of significant figures to which the value should be written. Then format. The format is given as general format or name the timing directories. So it will be named like, so if the time step for writing is 0.01, then time directory names will be starting from 0. 0 now we have in our case file. Then next one will be a folder named 0.1. Another will be a folder named 0.2. Then 0.3, 0.4, etc. If the time interval is 1, the folder name will be 0, 1, 2, 3, etc. And if we are giving a write interval as 10, then the name of the folders will be 0, 10, 20, etc. Now we are giving the runtime modifiable as true. That means I am giving some time step, and with that time step, we cannot solve that problem in a convergent way. So if it finds like that, that means if in that will be occurring only in the case of a transient flow. Okay, that will be occurring in the case of a transient flow, and in the transient conditions, since it's changing with respect to time, if I'm giving a time interval as 1 second, there are a lot of parameters that will be changing within the 1 second. Okay, within fraction of seconds, there will be a lot of things that's happening. So sometimes the current number goes on increasing. So in order to reduce the value of current number, what we want to do is that we want to reduce the time interval. Okay, that can be given as 0.1 or it can be given as 0.01. So that means we need to do it manually. Okay, we need to check the current number and correct it manually. So that will be quite difficult for us. Each and every time we need to look whether the current number is increasing or not. So without doing that, I am giving control to modify the time interval. Okay, I am specifying some time interval, and if you find that this time interval not good enough for convergence, you can modify the time. Yeah, sure. Sorry, I forgot that while uh, browsing that website. Then again, I forgot to change that into a presentation mode. Yeah, next question. One doubt regarding core number. Yeah, you can ask.
No, sir, actually, I did two simulations, one in ANSYS Fluent and Piso Solver, and other one in OpenFOAM Piso Form.
Okay.
And I used 0.01 as time step size in ANSYS, but the same time step is not working with the OpenFOAM. It is like the current number is increasing and it is exiting.
Yeah, and that particular case, that might be the problem with the mesh. either we want to change the mesh elements. That means it needs to be.
Actually, I exactly used the same mesh for both the simulation. One with MSH and the other one I converted from MSH to OpenFOAM mesh and tried the same settings.
But since this numerical scheme and all are different in using this ANSYS and OpenFOAM, so we may find this difficulty in this. So generally, what we do is that either we reduce the time step, or we
Yeah,
refine
I
the mesh.
tried reducing time step and it worked fine. But the thing is, like both are piezo algorithm. I run the pressure
Yeah.
velocity coupling, both are in piezo, but still,
Yeah, algorithms are same, but probably this numerical scheme will be different. That's why.
okay, okay, okay. Thank you.
Yeah. Now we can move to next slide. So we have discussed about the surface feature extract and all. Then comes the boundary conditions. So we have three patches now. That is full inlet, full outlet, and full wall. Then in the inlet condition, we are giving a surface normal fixed value. Okay. That means the fluid is entering perpendicular to that plane. Okay, because sometimes if I am having a pipe bend of 45 degree, that may not be perpendicular to any axis. Okay, that particular inlet plane cannot be perpendicular to inlet the x or y or z axis. So that we cannot give the direction of velocity as x coordinate some value and y coordinate and z coordinate 0 0. We cannot give it like that. Okay, so in that particular case, I am specifying that the air or the whatever the fluid may be, that fluid is entering perpendicular to that particular inlet patch. Okay, so that's why we are specifying it as surface normal fixed value. The value is fixed and it's entering perpendicular to that. Okay, just because the direction is just opposite to the axis. Okay, that we want to check in our case. Okay, sometimes it may be opposite to the axis or it will be in the direction of the axis. So that we want to check that. And if it's in the direction of the axis, obviously we want to give the values 1. Okay, or else if it's opposite direction, now, so that's the vector value, that's it. Now, in the case of outlet, we are giving the zero gradient because generally for solving a fluid problem, we have two equations, continuity equation and moment equation. This continuity equation will be having the velocities and the moment equation will be having pressure and velocity values. So for solving this pressure and velocity values, we have two equations and two sets of variables that we can take. Okay, the velocities are there as in three directions are there, that is u, v and w is there. But generally I will call it as u itself. So we have two variables and two unknowns. So for solving that we have two equations also. Okay, so if I am specifying the velocity at the inlet and outlet, it's not possible for us to solve. Okay, it's not possible for us to solve because in the inlet I am specifying as 10 meter per second. Outlet I am specifying it as 9 meter per second. It can have n number of solutions for pressure values. Okay, so we won't reach anywhere. The answer that we are getting will be wrong. So what we do is that either we need to specify velocity at the inlet or outlet, and the other value, that's pressure, should be specified just opposite to that. Okay, that means if I am specifying in velocity at the inlet, I need to specify the pressure at the outlet. So accordingly, the pressure will be adjusted or the pressure will be calculated for the inlet and velocity of the outlet will be calculated according to the pressure value at the outlet. Okay, thus we will be reaching the correct solution. So that's why we are giving the outlet velocity as zero gradient. We are not specifying any value. Then full wall, that means the wall region, we are giving no slip condition. That means there won't be any velocity. Velocity will be zero at the wall. So we are giving it as fixed value. Fixed value means the value is not changing. And we are assigning the value of 0, 0, 0. Okay. So this is about the boundary condition of, for the velocity. Now, next is the case of pressure. See, in the pressure, we are giving the inlet value of zero gradient because we are not specifying the pressure value since we had already given the velocity value of the. Now, in the case of outlet, we are specifying it as zero. That means ambient. Okay, the pressure is gauge in this case, particular case. So, gauge pressure, 1 atmosphere of pressure is in terms of gauge pressure, that's zero. Okay, so I'm specifying it as zero. That means the fluid is going out at atmospheric pressure, and in the fluid wall also I am specifying as zero gradient. So it will be calculated accordingly. So that's about the pressure values. And in these two cases, you can see one thing. In the internal field, I am giving the value of uniform 000. Okay, in the internal, I am giving the value of 000. And in the case of pressure file also, you can see that the value is given as 0. That means inside all the nodal points, I am specifying the value of 0 initially. Okay, as an initial condition, the value is given as 0. You can give any value. It doesn't matter. Okay. So that value, particular value will be taken for solving the equations initially. Then it will be comparing with the previous values and again the iteration happens. That's it. So if we know what should be the expected value at those points, we can give some values near to that so that we will be getting the result soon. Okay, or we'll meet the convergence easily. Okay. So what we
Sir,
used to do is, yeah,
sir, in this file, dimensions it is given as 0, 2, -2. So
yeah,
for pressure, the dimension will be
yeah. It will be meter square per second square.
pressure will be force per area. No? So
Yeah,
kilogram meter
the
per second square by second
density.
square.
We are dividing it by density.
Okay.
Okay, that's why we are getting like this.
Okay, sir. So
Okay.
in all the cases, we need to put the dimension like this.
Yeah, yeah, we need to do the dimension like this. In some
Then
cases,
we
we
can.
can see. Yeah, in some cases, we can see the pressure value as Pascal itself. So in that particular case, we can directly the value. But in this particular case, it's divided. That's right.
Okay, sir.
Okay. Yeah. Now, yeah, one more thing was there. Yeah, in the case of nu tilde, we are giving the inlet condition as free stream, and the value is being assigned initially as 0.14. It's a free stream value. Outlet although that's free stream, that's free to flow. Then wall, it's a fixed value because there is no slip condition is given at the boundaries. That's velocity zero over there, so there won't be any flow. So the value is given as 0. And in the case of nu t also, the same thing is being given. And in these both cases, the initially the value is given as 0, but at the walls, it has its own models that already I had shown some models in the case under this turbulent model. So we can specify either of these any of these models, and we can use that or that model has some equations for finding the value of nu t and nu tilde at the walls. Okay, so initially just we are giving the value of 0 itself.
Sir, one doubt. In the
Yeah.
previous slides,
Mhm. Yeah.
previous, sir.
Uh,
So for
in
the
the case of,
last one, this for velocity, this is mu tilde.
yeah, okay.
This is for viscosity, no, sir.
This is for viscous. No, no, no.
Turbulent
This is for finding the turbulent kinetic energy.
kinetic energy.
Yeah.
Okay, sir. So for turbulent kinetic energy, full inlet, what is that uniform value? Free stream velocity is given.
Yeah, free
Inlet will
stream
be
velocity
free
is
stream.
given. Yes, inlet and outlet, its flow is occurring. So that's why we are giving us free stream value.
And in wall, it is assumed to be 0.
Yeah, we are assuming it as 0. The fixed value is given because there is no kinetic energy will be there. Already we are giving it as fixed value. The velocity is given as fixed value, isn't it? That means no slip condition. No slip condition is being given to the wall. So there won't be any velocity at the wall.
Okay, sir.
Okay. Yeah.
So for a moving fall condition, what should be the
Moving wall condition, we need to specify the velocity. at that particular wall region.
Okay. So for inlet, it is having uniform velocity. -1 is the direction actually representing
Direction, yes,
negative.
direction, yes, yes, yes. It's a
That
direction.
is in which direction it will be in this case.
Suppose in it's our pipe inlet is just opposite to the x-axis. Okay,
Okay.
that it's just opposite the direction of x-axis. So if I am giving the value as one, what happens is that at the inlet, from the inlet, the flow is occurring backwards.
That
Okay,
means, sir, if the pipe inlet or the pipe is extending towards positive x direction, if you are
we
giving
can give
minus
the
one,
value as one.
oh,
Then if I am giving it a, yeah, if the pipe is extending towards the x positive direction and I am giving it as -1, then that will go wrong because the backflow is occurring.
okay. So, sir, one more thing. For giving a particular gauge pressure, what will be the condition we need to get P at the P that in the pressure?
I didn't hear the voice. It was breaking.
Sir, if you want to give some gauge pressure value, instead of having atmosphere pressure zero, where we need to put this pressure value? If you have some outlet
We can
pressure,
give the value here.
okay. So here
Here,
uniform, in the
uniform,
outlet is
yeah,
given
we
uniform
can
zero.
give the,
Okay.
yeah,
Inlet zero
instead of
grading
0, we
means
can, inlet 0 gradient means we are not giving any particular value. The inlet value will be calculated accordingly.
according to the velocity.
Yeah, according to the velocity, it will be calculated. Because that will go wrong. If we are specifying pressure at the inlet and outlet,
Ah,
and the velocity is also specified, then what should we need to solve?
yes, sir.
Yeah. So either we need to give pressure at the inlet or outlet. And just opposite to that, we need to specify the velocity. If you are specifying the velocity and pressure, I am giving the inlet, I am giving pressure as 1 bar, and a fluid is having a velocity of 10 meter per second.
Yes.
Okay. And at the outlet, it can have the pressure 0 bar, zero point 0.1 bar, zero point 0.2 bar, or whatever it may be. And accordingly, the velocity can be 10 meter per second, 20 meter per second, 30 meter per second, or even 5 meter per second. Okay, there are n number of combinations will be there, and it will be solving, and we'll be getting some results, and it won't be correct.
Okay. So
Okay,
here the
but if
condition
you
is pressure inlet is zero, pressure outlet is
no
assumed
pressure,
is
pressure inlet is given as 0 gradient.
zero gradient. That is, we are not providing any
Gradient.
gradient. Pressure
Yeah, I'm
outlet is
not providing
assumed.
any value. Yeah,
Okay.
yes, exactly.
Okay, sir.
Okay.
So one more thing, mu T for mu T represents actually kinetic viscosity,
Dissipation of kinetic energy.
dissipation of kinetic energy.
Kinetic energy. Yes. We are giving the viscosity as a property. So we don't want to give in the boundary condition. That's a property of a particular fluid.
Hmm.
So in the transport property, we are specifying the density and the kinematic viscosity of the fluid. Okay.
Sorry, sir, I lost my connection.
Okay, okay, sorry.
So in mu
Yeah,
T,
any more?
can you explain once again, sir, mu T
Yeah.
in that case?
In new T, you were discussing about the kinematic viscosity value that we will be providing in the transport properties. Okay, so that's the property of the particular fluid, and that's given only in the transport properties. Okay, so that depends on the fluid. So now this nu T and nu tilde, we are discussing about the kinematic part. That means the turbulent motion, that is kinematic turbulent viscosity and the dissipation of the kinematic energy.
In case of fluent, what is the expression? It is K and epsilon, no, sir?
Yeah, yeah. K
K is
epsilon is there. K, yes. This is equivalent to K epsilon. Yes.
okay, sir.
Yeah. So, any more doubts? Okay. So if you don't have any doubts, we can wind up from here. And tomorrow in the morning session, we'll be doing the solution part. We'll be giving the boundary conditions and all, and we'll be running that. And later on, we'll be looking to the paraview for getting the results. Okay, that's what we'll be doing tomorrow. So by tomorrow, we'll be completing one problem. Okay. So if you don't have any doubts, we can stop from here.
Okay, sir.
Okay. Okay then. Bye.